Good morning, honors chemistry students. The next element that I would like to examine in our review of atomic structure and quantum mechanics is that of chlorine. Chlorine has an atomic number of 17, and the particular isotope that I'm interested in today, it has a mass number of 35. 17, once again, represents the Z value, which is also representative of the atomic number, which equals the number of protons, which equals the number of electrons, which in this case is 17. 35 represents what we affectionately refer to as the A value, which is the mass number, which is equal to the sum of the positively charged protons plus the neutrally charged neutrons that comprise the nucleus. In this case, we say there are 17 protons, and to determine the number of neutrons, we subtract the atomic number from the mass number, which gives us a value of 18. 17 and 18 is equal to 35. So that being said, we always identify the isotope based on the mass numbers. So we would refer to this as chlorine-35, which has a mass number of 35. We say that it's positioned in row 3, period 3, also known as period 3 of the periodic table, because it's got a sufficient number of electrons to fill the third energy level. We say that it's a member of column 17, otherwise known as group 7A. So it has 7 valence electrons, keeping in mind that the A elements are the representative elements. And as such, the representative elements have Roman numerals which represent the number of valence electrons. We say that chlorine is a member of the halogen family, which includes fluorine, chlorine, bromine, iodine, and astatine. So we say it's a member of the halogen family, which are all gases with irritating odors. Well, actually, in that family is bromine, which is a liquid which readily vaporizes, and iodine, which is a solid which sublimes from a solid to a vapor state. As always, we want you to represent the atom using the atomic energy level diagram, affectionately known as the AELD. To do so, you represent the nucleus with a box, which is split in two. The top part represents the number of protons. The bottom box represents the number of neutrally charged particles. We've already identified 17 protons and 18 neutrons that comprise this nucleus, so the mass number is 35. We now set out about the daunting task of representing the 17 electrons in chlorine, the first 2 of which go on the N equals 1 energy level and an S sublevel. Again, the N equals 1 energy level is historically known as the K shell. Once you fill the 1s, by the Aufbau principle, you proceed to start filling the second energy level, placing 2 electrons in an orbital on an S sublevel. Once the S sublevel is filled, you go to the next highest sublevel, which is the 2p, and by Hund's rule, we put 1 electron in each orbital of the sublevel before we pair them up. And now we have accounted for 10 of the 17 valence electrons. So we have 7 more to account for. So we start by the Aufbau principle, filling the third energy level, which gets 2, and the 3s, and then beginning to complete or fill the third energy level, the 3p sublevel on the third energy level by placing one electron in each orbital of the sublevel, and then pairing up those two, which leaves us with 2, 4, 6, 7 valence electrons, which is why chlorine is positioned in column 17 or group 7a. So the third energy level is the n equals 3 or M shell. And you can clearly see that it's got 2, 4, 6, 7 valence electrons. It has 3 lone pairs. Here, another lone pair here, and another lone pair here. And it's got one unpaired electron, one unpaired valence electron, which would enable us to predict that given that chlorine's a nonmetal, that it forms one bond because it can share that one unpaired valence electron with either a metal or a nonmetal. I want you to represent the number of valence electrons in the electron dot formula or electron dot representation, which would include the symbol for the element, as well as placing the valence electrons, 2 in the 3s, one in this 3p, one in that 3p, one here, and one there. So you can clearly see we have 3 lone pairs and 1 unpaired electron for a total of 7 valence electrons, which is why chlorine is identified as being in group 7 of the periodic table. As always, I want you to construct the orbital notation diagram for chlorine, which is it gives us a way of accounting for electrons and energy levels. Chlorine's a fairly good size atom, so we need a little bit more space. Energy is plotted on the y-axis, moving away from the nucleus. The Aufbau principle, once again, or Aufbau principle, means to build up. It's a German word that means to build up, which means we build the placement of electrons and energy levels that are closest to the nucleus first. So the first energy level has just an S sublevel with 2 electrons. So we have now filled the first energy level with 2 electrons, and by the Aufbau principle, we move to the second energy level. Quantum mechanics predicts that the second energy level has both an S sublevel and a P sublevel with 3 orbitals, one that lies along the X, one along the Y, and one along the Z axis. So we begin filling the second energy level by placing 2 electrons in the 2s. And then the 2p we start filling by Hund's rule, placing 1 electron in each orbital of a sublevel before we pair them up. So now we have completed filling of the second energy level, which holds 8. We've totally accounted for 10, and we've got 7 more valence electrons to go. So by the Aufbau principle, once you've filled the second energy level, you begin to fill the third energy level, which is also predicted to have an S and a P sublevel. Again, the P's orbitals lie along the X, the Y, and the Z. We place 2 electrons in a 3s, and then start placing electrons in the 3p. We've placed 5 now, and we have 2 more to place. So by Hund's rule, each orbital in a sublevel gets 1 electron before you pair them up. And you can clearly see that there are 7 valence electrons in the 3p sublevel, 3 of which are lone pairs and 1 of which is unpaired. Again, these 3 s electrons are these 2, and those 2. These 3p electrons are those 2, which are those 2. These 2 are these 2, which are those 2. And this unpaired electron is that unpaired electron, which is that one. Also, I I would be remiss if I didn't mention that the reason the electrons have opposite spins is because they have similar charges. And when you place two electrons in close proximity to one another in an orbital that are spinning, the electrons are spinning, they tend to repel each other, one spinning clockwise and the other spinning counterclockwise. The up arrow is viewed as being the clockwise spin, and the down arrow is viewed as being the counterclockwise spin. To write the address for these valence electrons, we would simply write it as the electron configuration. And the electron configuration is a shorthand notation for writing the address of an electron in an atom, a valence electron in an atom. We have two electrons in an s sublevel on the first energy level, so we'd write 1s2. We have two electrons in an s sublevel on the second energy level, so we'd write 2s2. We have 6 electrons in a p sublevel on the second energy level, so we'd write 2p6. We have 2 electrons in an s sublevel on the third energy level, so we'd write 3s2. And finally, 5 electrons in a p sublevel on the third energy level, so we'd write 3p5. So you'd read this 1s2, 2s2, 2p6, 3s2, 3p5, and the superscripts should total to 17, which is the atomic number. So 5 and 2 is 7, and 6 is 13, and 2 is 15, and 2 is 17. Again, we can use shorthand notation by recognizing that 1s2, 2s2, 2p6 is the configuration of neon, and then we're adding 3s2, 3p5 to the outer configuration. So this is our outer configuration, and it's interesting to note that each member of the halogens, including fluorine, chlorine, bromine, iodine, and astatine, all have an outer configuration of s2p5. Thus, they have 7 valence electrons. 2 and 5 is 7, which places them in group 7a. And last but not least, I want you to represent the Cartesian coordinate system. Representation, which consists of the xy plane, and in essence, we represent the first 2 electrons on the 1s orbital. I want you to think of that as a spherical orbital where the electrons can be anywhere within that region of space, and the vertex represents the nucleus. Once you've filled the 1s, you then set out to fill the 2s. Once the 2s is filled, you begin filling the 3 2p orbitals, one that lies along the x, one that lies along the y, and one that lies along the z. Whew. Should be using a straight edge on that puppy. So one lies here and here, right? And then we're going to place 1 electron in the 2py, 2px, 2pz, and pair those up. And then last but not least, we have to place electrons on the third energy level. So the next 2 go in the s sublevel of the third energy level. So we're going to place 2 there, like so. Those are your 3s. And we're going to extend the 2p orbitals with a dashed line, like so. It gets a little bit confusing, but if you stick with it, you should pick it up. We've got, goodness, 5 electrons to place. 1 here, 1 here, 1 here. Go back and pair them up by Hund's rule, and that's what the coordinate covalent diagram for chlorine looks like. From this element, we're going to skip argon and probably go to the next two elements, which would be potassium and calcium, before we get to scandium on the march over to scandium. Thank you and have a good day.